Okay. Let's continue the same example. So, right, where did it go? Yeah. So, I just wanted to pull up the instructions. We're still on this example. The question is, are G and H isomorphic? If not, you have to explain. If so, you have to give an explicit isomorphism. So, that's what we're doing. And, so yeah, let's take a look at D. Well, they've got 5 vertices each. They have 1, 2, 3, 4, 5, 6. This one has 6 edges. This one has 1, 2, 3, 4, 5, 6 edges. The degree sequence here would be 3, 3, 2, 2, 2. And the degree sequence here would be, see, the largest one is 3. I've got another 3, and then 2, 2, 2. And those are the same. It was 3, 3, 2, 2, 2, and 3, 3, 2, 2, 2. So what do we do? Out of these things that we just checked, if we found something that wasn't the same, then we would know the answer was no. Like if they had different numbers of vertices, or if they had different numbers of edges, or if they have different degree sequences, we would know immediately that the answer was no, and that would be our explanation. It's whatever was different would be our explanation. But they were all the same. And so then, does that mean that the answer is yes? Well, not necessarily. If you start to suspect that the answer is yes, then you have to start thinking about coming up with an explicit isomorphism. So maybe let's start thinking along those lines. And so when you do a problem like this, it's tough because if the answer is yes, you have to do something that's quite different from what you have to do if the answer is no. So you kind of have to think along 2 different paths at the same time, or maybe think along one path for a little while and think along another path. And what I mean is, the first thing we did is we checked a bunch of things where I'm checking, like, does this have the same number of vertices? Does it have the same number of edges? Blah, blah, blah. And those are all things that I would check if the answer... let me start over. Those are all things that could tell me definitively that the answer is no. If I found that they have different number of vertices or different degree sequences or whatever, I would know immediately that the answer is no. Those things can't tell me that the answer is yes. The only thing that can tell me that the answer is yes is an explicit isomorphism. And those are like the 2 thought paths that I'm trying to describe. We went down the path of trying to come up with an explanation for why the answer would be no, and we had some trouble. So now let's go down the path of trying to show that the answer is yes. Well, an explicit isomorphism means that I find phi of everything. So let me just take all the vertices here, and maybe I'll go in alphabetical order again. U, V, almost forgot my alphabet. W, X, Y. And let's try to do this a smart way. So the reason why isomorphic graphs have the same degree sequence is because if you look at if there is an isomorphism, if U, like whatever degree U has, needs to be the same as the degree of the image of U. So here U has degree 3. the image of U has to be a degree 3 vertex. So in other words, it has to be vertex number 2 or vertex number 5. And before I commit to this, let me say a word more. What is special about these graphs? One thing that's special is if I just draw a bubble around these 3 and a bubble around these 2, then basically the edge set is just, I have every possible edge from a vertex on the top to a vertex on the bottom. And I don't have any edges like between vertices on the top or between the vertices on the bottom. I only have edges that go top to bottom. So it's like there's these 2 sets of vertices and I have every edge in between. And I can think of H the same way, except the drawing is a bit different. These will be my 3 vertices. So this is like this, this, and this. And then the other 2 vertices, so it's a little awkward. Maybe I'll do this in red. Well, maybe blue is less awkward. This is blue. So those are my 2 vertices, and I have every possible edge between any vertex in this bubble and then any vertex in the blue bubble. So that's the way in which these 2 graphs are the same. And I can use that to guide me when I write the isomorphism. So basically, U and V were the 2. It was in the bubble that had 2 vertices. And basically, their images, I'm going to make their images 2 and 5. And the truth is, I hardly care which is which. So I'm going to do U goes to 2, V goes to 5. I could have switched these 2, actually. And W, X, and Y are going to be 1, 4, 3. And again, when you do this, you really should do a little bit of checking with your eyes just to make sure that you didn't miss an edge or anything. But, W and U is an edge. So here's W, here's U. So that's 2 and 1. 2 and 1 is an edge. And I won't check all of them, but we can check, X, V. X corresponds to 4, V corresponds to 5, and 4 and 5 are adjacent. So you can finish checking, but this is a valid isomorphism. So the answer is yes, they are isomorphic. All right. So let's talk about 2 more examples of this. And so the truth is, in general, this is a very hard problem. I'm not going to give you a problem like this to do that's really that hard. But in general, especially if you're talking about large graphs, because the graphs that we've been dealing with, I think these have 6 vertices, and all the graphs that we've dealt with so far have small numbers of vertices, and determining whether 2 graphs are isomorphic is not that difficult if the number of vertices is small. But if the number of vertices is large, like imagine a graph with 1,000,000 vertices, and then you try to look at a picture of this graph, and maybe it has so many edges that it just looks like a mess. And then I give you another graph with 1,000,000 vertices, and it has so many edges that it looks like a mess. How would you ever look at those 2 and determine whether it's isomorphic? This is a problem that's very hard for humans to solve, and it's also hard for computers to solve, at least currently. There's a lot of current research going into the graph isomorphism problem. And you can Google that phrase, graph isomorphism problem. And this is a big problem that's being worked on currently in graph theory. Is just finding efficient algorithms to determine whether two large graphs are isomorphic or not. But like I said, I'm not going to give you one that's super hard. I'm not going to give you one on a million vertices. I probably won't even give you one on 10 vertices. Although, well, my last example actually has 10 vertices, but I won't go too high. But I do want to talk about more abstract things to look for to prove that the answer is no. Because from what we've been over, what would be your strategy for doing one of these? We went over the easy things to check. Like the first thing we check is whether it has the same number of vertices, number of edges, and degree sequence. But what if they do have the same number of vertices and edges and the degree sequence? Then, well, in the past, then we just started trying to find an isomorphism, and in the example that we did, we found one just fine. But what if you're having trouble finding one? Like, what if they have the same number of vertices, edges, and degree sequence, and then so you try finding an isomorphism, and you just can't figure out which vertex corresponds to which other vertex, and you're still not sure whether the answer is yes or no. What can you do? One thing you can do is just try harder. That's always an option, to just try to find an isomorphism a bit harder. Of course, you can, in the end, you can list every possible bijection between the two sets of vertices and check whether each one is an isomorphism. Of course, you'll be checking for a really long time, but that's something you could do. But anyway, I'm rambling a little bit. What I'd like to talk about specifically is more complicated ways that you can prove that the answer is no, to prove that two graphs are not isomorphic. So, yeah, I had something written. Here we go. So, at the top, we have a fact. So and it's maybe slightly technical or abstract, I should say. But if G is isomorphic to H, this is the symbol for isomorphism, by the way, so G is isomorphic to H, and P of X is a statement about graphs, so assume that capital X is a graph, and P of X is a statement about a graph. For example, it could be any statement. It could be the statement, this graph has 5 vertices, or it could be the statement, this graph has 10 edges, or this graph has a vertex of degree 7. These are statements about graphs. And in particular, if it's a statement that doesn't use any unquantified variables, a quantified variable is like when you say for all x or there exists y. The symbols, where can I go here? Yeah, these symbols, if you recall, are called quantifiers. This one means for all, this one means there exists. And if I say, for all v in the vertex set of x, this is a quantified variable. It would also be quantified if I wrote there exists instead of for all. If I don't have one of those, then it's an unquantified variable. So what I'm saying is that if P of X is a statement about a graph that doesn't use any unquantified variables, all the variables that appear in X or in P of X are quantified, then we have that P of G is true if and only if P of H is true. And I'm not going to prove this, but it's true. This fact is also not strictly in the book, but it's true. You can use it to attack these types of problems. Since it's a bit abstract, let me talk about an example here. So suppose we have two isomorphic graphs, and P of X is a statement like this. There exists a vertex V in the vertex set of X such that the degree of V is 3. This is a statement about a graph X, and it only uses quantified variables. The only variable I see here is V. We're using the letter V to represent a vertex, and it is quantified. It has a quantifier in front of it. So then if P of X is this particular statement about a graph, and I have two isomorphic graphs, then P of G is true if and only if P of H is true. What am I saying more specifically? I'm saying that this statement about a graph just says that the graph has a degree 3 vertex. It has a vertex of degree 3. And so what I'm saying is that if I have two isomorphic graphs, then G has a vertex of degree 3 if and only if H has a vertex of degree 3. And down here, I have an example of two isomorphic graphs. I have not written an explicit isomorphism, but it's not too hard for you to show that these two are isomorphic. Maybe that's a good exercise for you to do at home, to try to find an explicit isomorphism from here to here. And for the statement that I was just talking about, P of X, I would say that it's true of both graphs. Once again, P of X is the statement, there exists a vertex in the graph of degree 3. And sure enough, here's, for example, a vertex of degree 3. And in this graph, here's a vertex of degree 3. So they're both true, and that checks out P of G if and only if P of H. They also could both be false, but for these particular graphs, it's both true. Meanwhile, if I talk about a slightly different statement, say Q of X, Q of X is just going to say the degree of W is 3. It's not saying for all W, it's not saying there exists W, it's just saying that the degree of W is 3. W is an unquantified variable here. So if we're talking about a statement that uses unquantified variables, then what we're talking about doesn't apply. This note doesn't apply. In other words, we don't get to conclude that Q of G if and only if Q of H for this statement Q. And indeed, Q of G would be false because this graph has a vertex whose name is W, and the degree of W is not 3. So this statement is false. H also has a vertex whose name is W, and it does have degree 3. So, right, we really don't have Q of G if and only if Q of H. One of them's true, the other one's false. And why is that? That's because we already know why. It's because this is a statement with an unquantified variable. And more intuitively speaking here, this is because isomorphic graphs aren't supposed to really care what the names of the vertices are. These are isomorphic graphs, but that doesn't mean that this vertex whose name is W has anything to do with this vertex whose name is W. In fact, if you do write out an explicit isomorphism, phi of this W isn't going to be this W. It can't be, because this one has degree 2 and this one has degree 3. If you write an explicit isomorphism, phi of this W is going to have to be a degree 2 vertex. It would have to be either this one or this one. Well, okay, maybe it could be 4. Actually, it can't, but not for this reason. So, right, if you're talking about a property that depends crucially on the names of particular vertices, then this note doesn't apply. That's not a property that's preserved by isomorphisms. But if it only contains unquantified variables, then it is preserved by isomorphisms. And when I say a property is preserved by isomorphisms, I mean that whenever two graphs are isomorphic, that property holds for both of them, or it holds for neither of them. In other words, P of G if and only if P of H. Okay, after all of that, let's finish this up. What you want to do with this one, I can give it away here. I could spend more time if I didn't want to give it away. We could spend some time trying to find an isomorphism, like try to find phi of x, phi of y, phi of z, and so on. I could even try sort of the same strategy we tried last time, where I identified two bubbles of vertices that were like special bubbles. I had the ones on the top and the ones on the bottom. And there's something special about this graph is that I have every possible edge from the top to the bottom. And I don't have any edges between two vertices in the top. And I don't have any edges between two vertices in the bottom. Every edge goes from top to bottom. And then if I were able to go over here and identify two bubbles of vertices, then that could help me do the isomorphism. But I'm gonna have trouble. So, yeah, I don't know. Maybe at home you can spend more time just trying, and there's a lot of things that obviously won't work. Like I can't just circle these three on the top and these three on the bottom. But you can try different things. But I can tell you're going to have a lot of trouble. So again, when you're doing these problems, it can be tough because, again, there's two paths. There's the path you take if the answer is no, and the path you take if the answer is yes, and they're different. And sometimes you pursue one path until you say, okay, this isn't working, let me try something else. But then maybe that doesn't work either, so then you go back to the first path and try harder. So let's try to prove that the answer is no. What you have to do is you have to think of a property that one graph has and the other graph doesn't have. One thing that you can look for that isn't too bad is to just look for, the name of these is subgraphs, but maybe I can just use a different word because we haven't formally defined this yet. You can look for smaller graphs that are contained in the bigger graph, like... And let me be a little bit vague here. Here I see a triangle. I mean, it's obvious why I'm calling this a triangle. It's three vertices that are all adjacent. This, and this. In other words, H has the following property. Let P of X, this is going to be a statement about graphs, let it be the property X, or actually let me say this more mathy. There exists 3 vertices, maybe A, B, and C, in the vertex set of X, such that they're all adjacent. AB, BC, AC are all edges in X. So that's the statement. It is a statement about graphs, and it only involves quantified variables. These A, B, and C, it has there exists in front of it. And P of H, as we discussed, is true. A could be 2, B could be 3, C could be 4. But P of G is false. There's no 3 vertices in this graph that are all adjacent to each other. One way to tell that is just check every possibility, but that's kind of boring. Another way to tell it is, say I have 3 vertices. How could I find 3 vertices here that are all adjacent? Well, let's say I'm trying to find A, B, and C in here that are all adjacent. If I just look at A and B, one of them has to be on the top and the other one has to be on the bottom, right? Because if A and B are going to be adjacent, the only edges go from top to bottom. So out of A and B, one of them's on the top and one of them's going to be on the bottom. But then where could C be? If C's on the top, then C doesn't have any edges to the top. If C's on the bottom, then C doesn't have any edges to the bottom. So it's not going to be possible for C to be adjacent to both A and B. So also you can just look at this and say you don't see a triangle. The graph is small enough where you can just check with your eyes that it doesn't have a triangle. So this is a property that should be preserved by isomorphism, because this is a property that only involves unquantified variables. And if G and H were isomorphic, then since this is a statement that only involves that only involves quantified variables, we should have P of G if and only if P of H. But we don't. For this property, one of them's P of H is true and P of G is false. So they can't be isomorphic. And that's what I was talking about. That is the slightly more sophisticated way to show that 2 graphs are not isomorphic. Now let me do the last one, and I'll do it kind of fast. Like this is definitely the hardest one. So I guess you can check the easy things. They both have 10 vertices. They both have, well, they have the same number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, they both have 12 edges. So, yeah, maybe I'll even summarize this. Same order. Same size. Let's check the degree sequence. Let's see. This has degree 3, 3, 3, 3. And then there's also some degree 2 vertices. There's this one, this one, this one, this one, this one, and this one. So that was 1, 2, 3, 4, 5, 6. And if you painstakingly go through here and find the degree sequence, you will find that it is the same. 3, 3, 3, 3. So there's 4 vertices of degree 3. And the rest have degree 2. 2, 2, 2, 2, 2, 2, 2. So where does that put us? Unfortunately, that puts us in this murky area where we still don't know whether the answer is yes or the answer is no. Okay, so I lied. I said I was going to do this one fast, so maybe I'll move back towards doing it a little bit faster. I just wanted to check the easy stuff. Of course, the next thing you could try maybe is to try to find an explicit isomorphism. You're going to have trouble finding one because there isn't one. But you can try. Let me give this one away. The answer is no, and I wanted to illustrate a more complicated property, and it's not that complicated. So let me explain what I'm looking at here. In G, what I notice is all of the degree 2 vertices, like this one, both of its neighbors, remember a neighbor of a vertex is just another vertex that it's adjacent to. So the neighbors of R are Q and S. Those have degree 3. And I can check that that's true for all the degree 2 vertices. So here's another degree 2 vertex, and its neighbors, Q and U, both have degree 3. Z is another degree 2 vertex, and its neighbors both have degree 3. T is a degree 2 vertex. Its neighbors both have degree 3. So let P of X be that property. Say we're talking about a graph X. For all vertices, say V, if the degree of V is 2, then all the neighbors of V have degree 3. That's the property that I'm talking about. And that's the property that G has. And the reason why I'm picking on this property is that H does not have that property. In H, here's two vertices that have degree 2, and they are neighbors of each other. So here's a neighbor of a degree 2 vertex that doesn't have degree 3. So P of H is false. But this is a statement that only involves quantified variables, like V is quantified, and technically in this wording there's I'm talking about a neighbor of V, but this is like, when I say all, that's like saying for all, and that's a quantifier. So V is quantified and the neighbors of V are quantified. So this is a property that should be preserved by isomorphism. And so if this property has different answers for G and H, if one of them's true and one of them's false, then they can't be isomorphic. So no, G and H are not isomorphic.